Next speaker, Professor Ramamurty from Singapore. Can we have the next slide, please?
Thank you.
You got it, okay.
Thank you very much, Mike. I would like to start by thanking Professor Tony Cheetham for inviting me to this workshop. This is my fifth one, participating over the past maybe 10 to 12 years, and Natalie for all the wonderful arrangements. So we are going to switch from theory to experiments, and from glassy state to crystalline state, and polycrystalline state in almost all the time. And also slightly boring metals, although they are still relevant for all your flights to go back. You will be flying in metallic containers. And mostly technology in terms of how we manufacture metals. I come from NTU in Singapore. Okay, so I was still telling Mike that we deal with crystalline materials and polycrystalline materials and metallic bonded stuff. So we take it that the crystal structure is something that is, if you take aluminum, it's FCC. If you take titanium at room temperature, it's HCP. So these kinds of things are things we can't change. So what then we really play around with is microstructure. Okay, so sorry, this is something that we have to get used to. So if most of the engineering structures, they generally mechanical performance is the key indicator when you design a car, aeroplane, a rocket, a nuclear reactor. And they depend on this microstructure. So as metallurgical engineers, we want to play God with the microstructure. We want to be able to determine what kind of microstructures come, because microstructure is what determines the properties. And the processing routes essentially determine the microstructure. Okay, this is something that, as a background, you have to remember. So now this is where it gets complicated, right? So I just talked about processing, structure, and properties, right? So and often it's not just one property. It's basically you are talking about strength, toughness, weldability, corrosion resistance, etc., right? And density, and the most important of all, availability and cost. So you change a little bit in the processing conditions, and the microstructural features can change dramatically as these things show, and as a result, properties change. So this is one thing that unless you have a very good understanding of all these connections, you can't really have an engineering alloy that is useful for you in the truest sense of the word. All right, so if you take conventionally manufactured metals, it's not the entire atlas. These are a few microstructures. They're relatively simple. Even if you take this one, this is the nickel-based superalloy. So the jet engines that you came in, or that powered the aircraft that you came in, they would have probably the microstructure of this. This is the nickel-based superalloy. And it's relatively simple, right? And if you look at it at a very broad scale, these are the tools we have to control the microstructure. Remember, I said microstructure is the real key. And so one is to change the composition. Then processing conditions. If you cool it faster, you can change the microstructure sometimes. You can get a finer grain size. And then the most ways we do is basically metallurgy is all said and done heat and beat technology, from 3,000 years or 4,000 years. We heat the metal and we beat it to get the shape. And so thermomechanical processing is one way to control the microstructure. So, right? And so that thermomechanical processing, for example, allows us to refine the microstructure. So this is a 5 millimeter scale, and this is a 20 micron scale. So you can see that as you go through the thermomechanical processing for a titanium alloy, you can actually refine the microstructure and homogenize. So this is something to remember, right? Now, so that's how conventional metal manufacturing works. But most of the people are now interested in additively manufacturing. So conventional manufacturing is you make a big casting, and reduce the size to make whatever needle or disc or whatever you want. In 3D printing of metals, we basically build bottom up. So we build at any time a voxel and build it in like nature does, right? So for metal 3D printing, you basically need an energy source because metals are high melting point materials. We take typically powders or wires, and then we melt them at a specific location, okay? So these are basically, there are there are bed fusion. So you spread the powder with a predetermined thickness, 30 microns, 60 microns, and then you take a laser and shine on it to melt it. There is another method called directed energy deposition. So most of the talk, we deal with a number of different 3D printing techniques, but most of my talk will be on this laser powder bed fusion technique. Here it is very quickly. So what you do is you basically spread a layer of powder, and then you shine laser on it to melt wherever your specific locations you want, and you keep building from bottom up to get the 3D product that you want, right? So the physics of this problem is quite complex, right? So basically you have all the 3 heat transfer mechanisms that are operational here, and then you have phase changes, not as my previous speaker talked about, from amorphous to crystalline phase changes, but melting to solidification, and there is also some evaporation that is possible, right? And then because of the laser beam doing this, you have also the fluid dynamics coming into play, right? So it's quite a complex process that happens here as you melt a voxel at a time and as you keep moving the laser beam, right? So the key parameters are growth rate and thermal gradient and undercooling. That is the thing. So next few slides I will walk you through. I know that I'm standing between you and your lunch, so I'll try to accelerate. So the growth rate and thermal conductivity directions can affect these things. So for example, here you see the very fine grains. This is a single melt, single track. But if you build on this, you can see that the microstructure, the grain structure is, very fine, whereas on the outside it's much coarser. So if you look at you build several of these layers, you see very complicated microstructures coming into play, right? When you 3D print a metallic material using laser powder bed fusion technique, you get a hierarchical microstructure, okay? Hierarchical structure features. So at the sub-micron scale, you have the cellular structures, and I'll talk a little bit about it. And if you do TEM on it, you will get very high dislocation density decorating the cell walls. At the, from tens to sub-tens of microns, you get this very complicated grain structures. And if you go much larger scale, you have these meso-structures, which are often hundreds of microns in scale. So you have these features, and all of them could influence your mechanical response. And I will try to illustrate that. So one of the most common features is this cellular structure. So if you look at transfers to the build direction, you see these cellular structures, and if you see along the build direction, they are all aligned, and the misalignment between them is very nominal. So these are basically solidification cells, and what happens is, this is, go back. All right. So these are 4 different FCC, face-centered cubic alloys, and you see cellular structures in all of them. But the length scales, for example, depending on if you do laser powder bed fusion, the length scales of these cell structures are about sub-micron in scale, 60.63 microns, etc. But if you do take the same austenitic stainless steel, this is a very common, very widely used stainless steel. If you, for example, and use a different manufacturing technique called directed energy deposition, you get a much larger cellular structure that is now about 6 microns. So there is an order of magnitude increase in the cellular size. There is elemental segregation, as these maps show, to the cell boundaries. So solutes segregate to the boundaries. And if you zoom in and look at it in a microscope, you will see a very large dislocation density decorating these cell boundaries, right? Now, why does this happen? Why do you have these cell dislocations happening a lot? So what you're doing is, at any given point of time, you're scanning one line, right? And then you come overlapping another line. So the already solidified material undergoes a serious thermal heating and cooling, thermomechanical cycle, right? Because it's mechanical as well, because it's already stuck to the substrate, right? And then you're coming and depositing another layer. So in all these things, this doesn't happen in conventional manufactured metal. It's all cooled at the same time. Here, you're doing repeatedly heating and cooling it, and because of that, there is quite a lot of stretching and contraction. It's fatigue. So not conventional fatigue that you think of, and as a result of that, that is what these simulations show, fairly substantial thermal cycles, and so as a result, you have fairly large dislocation debris accumulating, and these dislocations decorate the cell walls. Okay, now that is about the cell structure, and then if you zoom out, if you will, to a slightly different scale, larger scale, you see very, very complex microstructures. These are very difficult to understand. I think I showed you earlier a structure like this. And for example, depending on your scanning rate, you can see the grains are sort of tilting more into vertical direction, kind of power you use. And so these are not very easy to interpret microstructures, even for metallurgists who are well versed with this. And you can see these kinds of structures which are where the grains seems to be completely inhomogeneous, right? And then, so at least this, you can see that there are a lot of, for example, if you add particles to this, so this powder particle, we add nucleation things, carbides and ceramic particles, then you can actually force this, what we call columnar to equiax transition. Let me illustrate that with this particular thing. This is where we take iron and then we add aluminum to it. Our idea was to reduce the aluminum is lighter, so we want to have a lighter steels, if you will. So if you take pure iron, this tells you is all 001 orientation. This is all red, means this is all highly textured grains. So as you go, as you add more and more aluminum, you are essentially forcing columnar to equiax transition and finer grain size. So these are the things that are possible. The last one is where essentially if you switch, this is not our work, this is, I think, probably your colleagues in Australia. If you switch on ultrasound, you get very fine grains, but when you switch it off, it again gets into coarse structure. Okay, so the melt pool, if you take, so at any given instance, the melt pool is what determines its solidification characteristics determine the kind of microstructure that you get, and as illustrated with these kinds of examples. So whether it's a shallow one, as in the electron beam powder bed fusion, versus LPBF, where it's not so shallow, and DED is much larger scale, so it changes the microstructural characteristics. And we just wrote a nice review on this very topic. All right. Now, if you zoom further out, go to much larger scale, you get meso-structures. Okay? These are hundreds of microns in size. So here, for example, you can see the scanning is all in one orientation, and the grain seems to be, they're all textured in 001 orientation, and you see that they're at about 60 degrees to the scanning direction, right? Now, on the other hand, if you, for example, change the anti-parallel direction, the alternate layers, you get this zigzag kind of fashion. So you can actually engineer these meso-structures whose signatures are will be left with like this. Okay, now, so that just tells you the kind of microstructures that are possible. There are submicron scale, micron scales, and mesoscale microstructural features, and they all will obviously influence the mechanical properties. So we take one of these alloys. This is if you take the car engines, most of these are aluminum silicon alloys near eutectic composition, right? So if you take this alloy and just use casting, the strength, yield strength of that will be about 100 MPa, tensile strength will be 200 MPa, and about the reasonable ductility of about 10%. The same alloy, you make powder, you then print it, 3D print it using laser powder bed fusion. What you will notice is that the strength has more than doubled from 100 to 200 plus, right? The UTS has also gone up, but the ductility has really tanked. It's gone very, very bad. So, so the strength goes up when you 3D print an alloy, but the ductility comes down. That's the thing. So this is true also for 316L. It's an austenitic stainless steel. So again, sorry, this is not the, yeah. So this conventionally manufactured alloy, you can see it's fairly ductile, but if you do a laser powder bed fusion, basically the strength increases, but ductility decreases. So this is a general observation for most 3D printed alloys compared to their counterparts which are conventionally manufactured. Strength goes up, ductility decreases. What are the reasons behind this? So I already talked about the cellular structure. So one can say, okay, the length scale that determines the yield strength in the material is no longer the grain size, but the cell size. And you have also a large number of dislocations, right? So there are two theories or hypotheses. One says, okay, because you have this Hall pitch relationship. Any of you who studied material science would, Callister book would, this is first thing that you learn. So the finer the grain size, higher is the strength, because the grain boundaries act as barriers for dislocation motion. They do other things, as Stephen showed, but here also they actually, in terms of strength, they are very, very critical aspects. So this is the grain Hall pitch relationship here, and these Wang et al. Say that, okay, it's instead of the grain size, you fit in the cellular size. The other school of thought says, look, no, you have very large number of dislocations, and dislocations are the ones which basically hinder plasticity, and that's why you get the high strength. So what we did to resolve is basically we go and did this micropillar compression experiment. So we take focused iron beam, milling, and we mill out these pillars. You can see the cell structures, and then we compress them. Okay, so this is these are engineering stress strain curves, but these pillars are now 2 microns or 1 micron diameter, so very, very fine structures. So obviously you can see as the pillars get smaller, the black one is 1 micron, you see large serrated flow because of the size itself. More importantly, as the size gets smaller, it gets stronger. Smaller is stronger in this case. Okay, so we could actually machine out pillars with or without the cellular structure, because in the directed energy deposition case, we have fairly large cell size. We can have a pillar with a cell boundary in between, or a pillar without any boundary. So we can actually have a direct comparison of these things, and then here is the comparison, the last one. So they both are 2 micron pillars, and there is no difference. So whether you have a cell boundary or not doesn't seem to be affecting the property. Okay, and we did it for aluminum silicon as well. I skipped this. In this case, there is no size, smaller is stronger response. So here is the, we did a lot of different, materials, and this is a summary plot, if you will. So here, what we do is we take the yield strength that we measure. So for those of you who are not familiar, yield strength is when we have the elastic to plastic transition, the stress required to initiate plastic deformation in a metal. So now, that we normalize with the bulk value, taking a very large specimen and measuring that. So in this axis, we normalize the pillar diameter. Capital D is the pillar diameter, and with the cell or grain size. So if you have conventionally manufactured metals with microcrystalline or nanocrystalline metals, what you will see is that as the pillar diameter gets smaller and smaller, it's weaker. Smaller is weaker. But in 3D printed metals, it's smaller is stronger. You can see all of the cases, it's mostly smaller is stronger, okay? So why does this happen, okay? So I actually put this slide after listening to our chair's talk the other day. F.C. Frank is what he mentioned. He was at Bristol physics department. First thing to understand is how dislocations multiply. They do multiply dramatically. If you take a well-grown crystal and then metallic crystal and you squeeze it a bit, you deform it, they go by 6 orders of magnitude. Dislocations multiply. And they wondered very early on, all these condensed matter physicists wondered why this happened. So Frank came up, this is a fascinating story itself, that Frank and Reed came up with this idea on the same day, roughly same time, different places. So check out on the Wikipedia rabbit hole, on this, it's very fascinating. And then they met next week and then decided to write a paper together. So Frank-Reed source basically is if you have a dislocation line like this, if it's pinned on 2 ends, or it doesn't need to be pinned, but it can have only shear stress on this particular segment. So what happens is it's basically once you apply stress, it bows out, and after a while it becomes unstable and punches out a dislocation. And this is what you can actually see in this thing, right? So for those from Cambridge, materials department will recognize with Do-It-Palms thing. Will Klein started. So the stress required to operate a Frank-Reed source is basically inversely scales with the distance, the length of it, GB by D, okay? Now, so that is the thing. So what happens when you go to smaller and smaller diameter pillars is that it's not the full length. So you have what we call single arm sources, right? So this is basically, it's anchored at the surface. This is the single arm source, whereas this is the Frank-Reed source. So when the average length of the Frank-Reed source is much smaller, you need to apply higher stress for them to get active, and that's why the yield strength goes up, right? So when you go to larger and larger diameter pillars, obviously you have not these single arm sources, but the Frank-Reed sources themselves becoming, their contribution becoming dominant, and that's why you get bulk-like properties. In the aluminum silicon case, we have actually particles, silicon solubility in aluminum is very, very negligible. So it's all precipitates out as nanoparticles, and that's why you basically don't have, even if you go to 1 micron, you get as the bulk strength, okay? Now, so we basically, what is the reason that you get high strength? Not the cellular structures, but we did systematic experiments where we can actually vary these characteristics very systematically. And what we show is that it's all because of the dislocation density. So you have the cellular structures, but you also have very high dislocation density in this material, in the as fabricated state, right? As fabricated state, just because it's going through thermomechanical cycling. And this is from Taylor's calculation, and we show that we know the dislocation density. That is what I flashed in the previous slide, and we show that the additional strength actually comes from the large dislocation density. Okay. Now, early on, I summarized that when you 3D print a metal, the strength goes up. In metallic materials context, it's true that you can't have the cake and eat it too, right? So when your strength goes up, you have to give up something. And the trade-off that you do is with ductility. Okay, so the strength goes up, ductilities come down. Why does it happen? Because the same dislocation. So I told you that there is a large dislocation density in the material, and that increases the strength. But it's like a reservoir. Metal can only accommodate so many dislocations. It can't accommodate more. So because of the way you manufactured, you already stored in a lot of dislocations. So the further number of dislocations that you can add on to it is smaller. And that's why the work hardening ability, I'm sorry, it's a little more technical for this audience in this context, but work hardening ability decreases. So this is actually, there is a considered criterion that we teach. And so as the work hardening exponent decreases, the ability, this is uniform elongation, is the ductility of the material, and that reduces. So this is what it tells you. So the way you manufacture changes the whole game. The microstructures change, the dislocation densities change, and they alter both strength and ductility as we saw it, okay? And, but the cellular boundaries really don't stop, and that is what this picture shows. This is a well-polished tensile specimen. Then we basically apply 5% strain on it and look afterwards. Don't focus on these dots. These are silica particles. They don't really contribute to the strength. But what you can see is the slip traces, and you can see these cutting all the cell boundaries. So really the cell boundaries don't stop dislocations like red traffic lights that grain boundaries do. So treating them as grain boundaries is not correct. Okay, move on to fracture behavior of these materials. I talked about ductility and strength trade-off. It's really the fracture toughness and strength trade-off. So you need, for an engineering application, both these characteristics to be very good, especially fracture toughness. So when you design a critical component means a component that should not fail, okay? Why is it critical? So if you think of an aeroplane, no part of it should fail without telling you, okay? That's very bad news, because somebody told this. What excites scientists is that, pure science people, is that when they discover something unexpected. The classic case is Eureka moment of Archimedes. What excites engineers is that everything should work as you predicted them to be, right? So if an aeroplane takes off in Dubai, travels 12 hours to New York, it should land safely and immediately turn back and whatnot, right? So for that, engineering components should have damage tolerance. Any damage that is created during its service, it should be able to tolerate, so that we do periodic inspections and remove them, right? For that, you need also fracture toughness and resistance to fracture. That's why we don't use ceramic materials in structural components, because they don't have toughness. They have high strength and other properties. And unfortunately, the toughness and strength go in the opposite directions, as just illustrated here. Rob Ritchie wrote about this long ago. All right, so remember this slide? I told you aluminum silicon, when we 3D print it, the strength goes up, right? And I also told you that ductility decreases, and ductility and fracture toughness are generally correlated in a linear manner. So we were expecting that fracture toughness of this alloy would be disastrous, very, very bad. So for reference, the as-cast alloy fracture toughness is about 11 MPa root meters. This is a unique thing. So when we did fracture toughness measurements, we were expecting it to be much lower than 10 MPa root meters. What we found is that the fracture toughness actually did not decrease, but actually gone up. Strength has gone up by about 100%, but the fracture toughness has gone up by 300, 400%, okay? So these are what we call proper fracture toughness measurements, where we put a crack and measure these things. So why does this happen, right? So I told you that 3D printing is a bottom-up way of manufacturing materials, right? We basically build line by line, layer by layer. And what it does is impart a meso-structure. I also talked to you about it. And the strategy that we use to print leaves a signature in the material. Okay, this is the signature of this, the way we built this. And so each of these is one line, cross-section of one line, and you can see them overlapping, and then you rotate 73 degrees between successive layers, and you get these things. So what happens is that in this particular material, because silicon's solid solubility is very low, silicon essentially decorates these hatch boundaries, right? And so this is, so for example, you can see these boundaries. If you magnify it, silicon is rich, they become silicon rich. So what happens is if a crack comes along, it sees silicon is brittle, so it thinks, okay, I have an easier path, because, and it dives. And then it goes away from what we call mode 1 direction, right? So it has to go straight this way, and it just goes down. And coming back up is much more energy-intensive process. So think of it, those of you who run or bicycle, if it is a flat land, if you start from the same altitude, 10 kilometers, running or biking, you will, the kind of energy that you have to spend. For the same distance, same altitude, finish and end, but if it is highly corrugated, highly tortuous path, you will have to spend a lot more energy. Going down is easy, but coming up is much more difficult. It's exactly the same story here. And it's actually more three-dimensional in nature. So what happens is, these are the things, they're just schematic illustrations. So the cracks get deflected, and this crack tip tortuosity, tortuous path in 3 dimensions is, as these fractographs illustrate, what causes the fracture toughness to go up a lot. So the strength goes up because of the microstructural reasons, high dislocation densities, etc. Whereas the toughness improvement comes about because of the meso-structural features. So if you again look at the fracture toughness, yield strength thing, the expectation is to go like this, but we are actually able to push the other way around because of the way you manufacture these things, the signatures they leave. Okay, so how do we control the meso-structures, right? Next question is, if they improve the fracture toughness. So, for example, if you can, depending on the powders, for example, if you do fine powders versus coarse powders, the scale is similar, but you can see these are much coarser powders. So the meso-structure is hard to see, whereas you can see very clearly here. And this is a mixture of fine and coarse powders, right? And even the grain features are very different in these materials, okay? Now, so in fact, my former postdoc worked on this, and we published a paper in Nature Com, on this. So, for example, if you polish this 3D printed piece of metal, you can't see this. But if you basically etch it, because of the different grain structures, you can see this NTU things by varying these things. So you can essentially, early on I told you, right, we want to play around with the microstructures. We want to be able to do whatever we want, and this is one way, right? If you take titanium 6, aluminum 4, vanadium, this is a very, very important alloy. So when you, again, aeroplanes, the front, these big blades are made of Ti-6-4. So if you, for example, use 30 micron layer thickness and a scan rotation of 90 degrees between them, you get these square grains on the top surface, and the side, these are all columnar. So epitaxial growth actually exists because the layer thickness is smaller. Now, if you, for example, change this from 30 microns, you still keep it. You change it to 67-degree rotation between successive layers. On the top, you break that square grains, but on the side also, columnar grains are broken, but still the grains are oriented in one way. Now, if you, for example, increase the layer thickness to 60 microns and do the scan rotation to 67 degrees, you will be able to break these square grains and columnar grains. So you basically, by changing this, the alloy is the same. We didn't change the composition. We can also change the composition and do these things. But by playing around with these, the print strategies, process parameters, if you will, you can essentially get the meso-structure that you want. Okay. We measure the mechanical properties. In this case, one of the other things that happens is because you are at any given instance of time, you're melting a very small voxel of material, and it is sitting on a huge plate of, so which rapid solidification conditions prevail, and you get martensitic metastable alpha prime microstructure here, and that essentially gives this very high strength in to this material. And now I have 3.3 minutes left, and I'll talk about this high entropy alloys. So, what are high entropy alloys? Basically, Brian Cantor and they came up with this idea. So, I talked about all this 316L and whatnot, where we add a specific amount of chromium for corrosion resistance, a specific amount of nickel to keep austenite, etc. So we basically previously used to play around with these ends if you take a ternary alloy systems. Now, why not go to the center of it? So that is the kind of idea. And these alloys seems to have caught the fascination of all the metallurgical community because they have a lot of interesting mechanical properties, including good strength ductility balance. Okay? And in terms of hydrogen embrittlement resistance, they seem to be very good. All right. So these alloys, this is not our work, Rob Ritchie's work, seems to have world record numbers for fracture toughness. So these are, you can see here, the fracture toughness values are 500 ampere root meters, and especially very low temperatures. So these, steels will have maybe not even 100. So this is like 500 ampere root meters, very, very large. And that's how they got into Nature kind of papers. So FCC-based ones have, the issue is they have not much strength, but very high fracture toughness values. So when you 3D print these metals, so the strength, again, goes up. But this is a cobalt, chromium, nickel, equal amounts. So the strength goes up, whether you do the testing at 298 or 77 Kelvin. And this happens because, you have twinning and other mechanisms coming into play. But what is interesting is if you take this and 3D print the alloy, basically you get the high strength, but fracture toughness seems to be slightly reducing, right? So the blue is a slight reduction compared to the wrought alloy. Now, we slightly altered the composition, cobalt, chromium, now you added nickel, iron and aluminum. So what happens in this case is, you can see these pictures here, there are these nano bridges, which are dislocation stuff. This is schematically illustrated here, right? So what happens in this material is when you do tensile testing, the strength is much larger at 77 K compared to the conventionally manufactured alloys. So there is a 50% increase. In addition, there is a substantial improvement in fracture toughness. So these are the fracture toughness values you can see. So at 298 room temperature, it's 306. And even at 77, you still have very high fracture toughness, 300 ampere root meters. These are very, very high numbers, right? If you just heat treat it and get rid of all these nano bridges, obviously everything tanks, goes back to very poor values. So this is where they are. So compared to the cryogenic steels and other materials, these 3D printing techniques, which gives you these nano bridges, essentially gives you very, very good properties. And these pictures illustrate these bridges essentially bridge the cracks from propagating and give you very high toughness. All right, my time is up. So what I will do is, there is unnotched fatigue. I won't talk about this. Go to the last slide, hopefully. Yeah. So what hopefully I illustrated to you is that, when you do 3D print a metal, which is a bottom-up approach, you get very fascinating microstructures, which are hierarchical in nature, a lot of dislocations, etc. So we're kind of figuring out how we can control them. I have illustrated that aspect as well. And because of that, you get unique combinations of properties, both strength and toughness simultaneously increasing. and which is very, very good. Okay, so early on, I talked about this processing, microstructure, and mechanical performance connections. Right now, for this microstructure, we have to add all these additional features, meso-structures, etc. The thing that I didn't get a chance to talk about is the porosity. I skipped on fatigue because that also affects the properties quite dramatically. And then because of the rapid solidification conditions, sometimes you can also get metastable structures. And that's another play you have. So the degrees of freedom that you have in terms of microstructural control increase substantially. And because you are printing 3D components directly in like a one-part synthesis that chemists talk about, you can actually have structural components with bespoke microstructures that are specifically designed for that very purpose. With that, thank you very much for your attention.
Thank you. Great talk. Any questions from the audience? Anybody?
Everybody's probably
Stephen,
hungry.
yeah.
Thank you. Very nice talk.
Thank you.
I learned a lot, actually. So these so-called high-entropy multi-component metals actually some of them form glasses quite easily, at quite low print rates. So can you make a glass by this 3D printing this way?
I think the 3D printing itself will not allow, because even if you form glasses, they will be metastable, and so they will crystallize rather, after, because of the repeated heating. So if you take good glass formers, the zirconium-based alloys, bulk metallic glasses, if you do 3D print, sometimes they can crystallize. But high entropy metallic glasses is something that people are talking about, and some of the people are investigating, So 3D printing glasses, I'm not particularly fascinated about, because one of the, if you look at glass, the nice aspect about it is you go to the glass transition, or supercooled liquid state, and you'll be able to give all kinds of shapes, right, to glasses. You look at your very fascinating perfume bottles; they are all glass forming ability. I have another, I before I got into this bandwagon, I was doing metallic glass work a lot. So, okay, yeah.
Look, I think anyone in the audience that flies will be grateful that people are doing research on this kind of work for planes.
Yeah.
And so I always wonder, is this plane going to survive? How many times has it flown? But I guess I'm fascinated by the 3D printing nature. Can you see that being a manufacturing technique that will go into making components for aircraft?
Yes, it will. Yeah, it will go for specific components. So this, it will go in for sure. Will it be generic? So the thing is, most of even advanced metals, right, are very cheap. This is one thing that people have to appreciate. Really inexpensive. So I spent a summer at Exxon, and one of these leaders told me, Ram, these pipeline steels, very, very advanced pipeline steels, do you recognize that on per kilo basis, they're cheaper than sugar? Per kilo basis, advanced steels. This is not just regular low carbon steels. So they will find niche applications, will be used, but no, in terms of there are one of the things that I skipped is fatigue aspects. So there is a great challenge in terms of certification of these components for long-term use. They are being used in rockets already, but for aeroplanes, still, it's a question. Yeah.
Bring the
I
session
see Tony
to
giving
the end, because we have a photograph, right?